We are going to start with a review on bonding, the different models we know about bonding in molecules, and then we'll talk about a new theory for bonding called MO theory, or molecular orbital theory. So to begin with, just going over the different kind of bonds we know, we recognize ionic bonds here, right? Interaction between cations and anions, right? An electrostatic attraction. We have molecular compounds with their covalent bonds. That's what we're going to be talking about today. Those are shared electrons, right? And then in metals, we have these metallic crystals, where what we think of these as positively charged nuclei with a sea of electrons, mobile electrons moving around. So these are the electrons zipping around here, right? And that gives us this is why metals are really good conductors, right? If conductivity is movement of electrons, we can see these electrons are able to move. If we think about valence bond theory, this is we're taking atomic orbitals like S's and P's and D's and F's. Really, we're mostly interested in S's and P's. We're taking these and we are having them overlap to form bonds. So if we look at these two hydrogen atoms here, right, both with electron configurations of 1s1, as they approach each other, well, to begin with, when they're infinitely far apart, there's no interaction between them, right? They're not attracted, they're not repelled. As they get closer together, right, as the distance decreases, they start to interact with each other. And what's happening is the positively charged nucleus in one proton is starting to interact with the electrons of the other hydrogen and vice versa. And when they get to a perfect distance, in this case 74 picometers, you have the hydrogen-hydrogen covalent bond formed. And this is where we go from high energy or no energy here down to a lower energy, more stable. Remember, in chemistry, energy diagrams, lower on the diagram means more stable, higher means less stable. And then, as we know, if you get closer, they start to repel each other, right? The positively charged nuclei start to repel each other, and you get higher and higher energy, less and less stable. So there's a nice sweet spot where you can form this covalent bond between hydrogen atoms. When we draw this using valence bond theory, typically what we do is we have one hydrogen with his 1s orbital and electron, the other one with his 1s electron, and as they get closer together, what we draw is we just draw them overlapping. So this represents this. And this bond we know is called a sigma bond, right? The direct overlap of electrons that are approaching each other, or between atoms. So we can do the same thing with HCl. H again has a 1s1 electron configuration. Cl is a little bit bigger, so he is going to be neon, and then 3s2 and 3p5. So the valence, or in the n equals 3 valence, so chlorine can use s orbitals or p orbitals, but which one needs an electron? It's a p orbital. So the way we would draw this is H is going to have his s orbital. We take chlorine with his p. They're going to approach each other, right? And you're going to get this overlap. And this is the H. This is the chlorine atom there. Here, let's put some black dots on there so we can see. So here would be the hydrogen nucleus. Here would be the chlorine atom. And together there we formed a sigma bond again. So this is between an S and a P. So we can have sigma bonds between those. You can also have sigma bonds between two P's, S's and P's, and various things. We'll see examples of that. All right. So again, looking at our model here. So if we're going to use valence bond theory to draw a bond here, we have an H and an H, right? These guys are going to approach forming a sigma bond. That makes sense. H, F. F will use a p orbital. So we have an s orbital from H, and we'll have another p from F. That's another sigma bond. Let's take a look. Here's carbon. He's making 4 bonds. So what orbitals do we have available? We have S's, right? And those can overlap directly like we've seen. We've got P's, and they come in 3 different orientations, don't they? So one straight up and down, one to the left and the right, and one sort of in and out of the page. And I believe we call this one PX, we call this one maybe PY, and this one's PZ. Not super important. But what's the bond angle with these guys. That's a 90-degree angle. This is, we know from experiment, this is 109.5 degrees. So that we have a problem. If I use, let's see, for carbon it's 1s2, 2s2, 2p2. So I have an s orbital and then I've got the 3 p's. All right, I put electrons in there, following Hund's rule. Okay, well, let's say I use my p's to form sigma bonds with h's. Here's going to be one p orbital, right? Carbon's in the middle here. That can be a sigma bond between C and H, maybe this one. All right, then I want to draw another one, and so the p orbital is going to be perpendicular to the first one, right? Like this. These guys are perpendicular to each other. And if I do that, I used to be able to put this thing away, and I can't do it now. Weird. Oh no, cancel. Oh, no. Turns out I haven't made a video in a while. Here we go. So if I do that, I get a sigma bond here. That's 90 degrees. That is not 109.5, so we have a problem. And so what we're seeing is that valence bond theory, where we're using atomic orbitals, S's, P's, and D's, to form bonds, fails here. What's the bond angle here? 120 degrees. That's not 90 again. Here is, what's that bond angle? That would be 180 degrees. Well, if you considered this pair of electrons in its own orbital, that's also not 90 degrees. So we have a problem. And we solve that problem by using hybrid orbitals.